This is Dr. Chris Hill, and welcome to Math 4150 Linear Algebra, Upper Level Linear Algebra. Welcome to the Spring 2021 semester. This is a VCon class, but it will be meeting face-to-face in Math 103, which is our video conference room on the Macon campus. Right now, we don't have any students on the Cochran campus, so we're only on the Macon campus, but unless they send us home due to COVID-19, we will be face-to-face starting on Wednesday, January the 13th. As you've noticed in the Brightspace and your syllabus, Brightspace is set up as if it were an online class, and that is on purpose, just in case they send us home due to the pandemic. But we will be in class face to face, but I will be asking you to turn your homeworks in the assignment tool in Brightspace or D2L. And here is my intention to make a weekly video to upload into Brightspace corresponding to the lectures in the face-to-face meetings that we have. So once again, I know you've all had the lower level Math 2260 linear algebra. It might be a while for some of you, but you are familiar with what the content is, generally speaking. Linear equations, and in 2 space, straight line, and 3 space, a plane. And generally speaking, if you go beyond 3 dimensions, we would call the graph of a linear equation a hyperplane. And they all take place in the context of vector spaces. Now, you may remember that you also learned a lot about vector spaces in Calculus 3, especially there in R3 in 3 dimensions, and other classes as well. Vector spaces are foundational to many disciplines in mathematics. So having looked at your syllabus in the day-to-day course outline, the first lecture is from Chapter 1 and Section 1, and I do have a PDF version of our textbook located in Brightspace for you. And starting in Chapter 1, Section 1 today, we're looking at definitions concerning vector spaces and the scalar fields over which they are taken. So without further ado, let's dive right into it, starting on page 2 of our textbook, Definitions. Now, before we talk about a vector space, we just briefly touch on the definition of the scalar field over which the vector space will be taken. All of us, of course, know all about the real numbers and the complex numbers, but it says let K be a subset of the complex numbers, C. Now, this set K doesn't necessarily have to be the complex numbers. It could be a more abstract set, but in the context of linear algebra, it's either going to be the real numbers or the complex numbers. But here's the general definition of a field, and K being a subset of the complex numbers. We say that K is a field if it satisfies the following 3 axioms. If x and y are elements of K, then the sum, x plus y, and x times y are also elements of K. Those are known as closure axioms. When we say that a set is closed under the operation of addition or multiplication, that's what we're saying. We're saying that if you take 2 elements in that set and you operate on those elements with some kind of addition or multiplication, then the outcome of that operation is still inside the same set that those two elements are in. B, if x is an element of k, then the additive inverse minus x is in there. And if x is not 0, then the multiplicative inverse is in there as well. And then third, the elements 0 and 1 are in the set K. So clearly, the real numbers and the complex numbers fit this definition of what's called a field. If you go to grad school and you study abstract algebra, and I know that we're offering abstract algebra this semester online, but there's a branch of abstract algebra called field theory, and it's a whole semester study, and we're only getting a glimpse of it right now with its definition. Now, we denote by the letter Q the set of rational numbers, that is the set of fractions where m and n are integers and n is not 0. We all know we can't divide by 0. That's easily verified that the set of rational numbers is a field with those three axioms. But note that the set Z of integers is not a field because the second condition is not satisfied. It would not be closed under, for example, a multiplicative inverse. It's not closed under multiplicative inverse for non-zero elements. So the main thing to know about a field is that it behaves according to the ordinary rules of arithmetic, addition and multiplication, and that we use in the real numbers and the complex numbers. Now, that's all we really need to know about what is a field. Again, if you want to know more about what a field is, you would take more about that probably in grad school. But in linear algebra, we may restrict our attention to either the real numbers or the complex numbers. Now, whenever we talk next about a vector space, in a lot of the context, especially in the theorems, we'll just use the abstract letter K, and it could be the reals or it could be the complex numbers. But there'll be many cases where we'll specify that here we're working with the real numbers or here we're working with the complex numbers. And so we use the field to get the scalars or the numbers for our vector space. And the word scalar comes from the geometry of a vector space. When you multiply a vector by a number, what does it do? It scales the length of that vector, doesn't it? So that's where the word scalar comes from. So what is a vector space? Well, a vector space V over the field K. It is a set of elements or objects or vectors, if you will, that can be added and multiplied by elements of the field K, first in such a way that two closure axioms are true. You see in my handwritten notes here on the right side of your screen, the first two, or really three axioms, A, B, and C, that I have handwritten. We start with a non-empty set, V, and a scalar field K, and then we look at these closure axioms. If we have three vectors, U, V, W, in V, and A, B, and C are scalars or numbers, And then first, if u and v are in V, then the sum of u plus v is an element of V, and scalar multiples c times v is in V. Okay? So we say that a vector space is closed under vector addition and scalar multiplication. Now, those closure axioms also necessarily mean that what we call the zero vector is also in the vector space. Now, with those two closure axioms come the 8 axioms found on page 3, VS1 through VS8. So looking at the vector space axioms now, 1 through 8 here on page 3, in addition to the two closure axioms, all 8 of these must be satisfied before we have a vector space. So again, if you take 3 vectors, u, v, and w in the vector space and scalars a, b, and c in the field K, the first one is the associative property. It doesn't matter how we associate the elements when we add them together. Remember that the operation of addition and of multiplication is a binary operation that you only do on 2 elements at a time. So you only add 2 elements at a time. So it doesn't matter if you add u plus v and then tack w to it, or start out by adding v and w and then tack on u to it afterward. It's the same thing, isn't it? The associative property. The second axiom tells us that we have a zero vector in our space denoted by the bold letter O, or if I handwrite it, I use the Greek letter theta. It's the additive identity. 0 plus u equals u plus 0 equals u for all elements u in V. The third one is the additive inverse. For every vector in the space, it has a unique element called negative u or minus u, so that when u is added with its additive inverse, we get the zero vector. 4, we have the commutative property that u plus v is the same as v plus u. And then 5, 6, and 7 are the distributive properties. Distributive property over addition and over scalar multiplication. C times u plus v is cu plus cv. And then if you have 2 scalars, a plus b times v is av plus bv. Or number 7, if you have 2 scalars, a and b, times vector v, it doesn't matter where the scalars are, they can go anywhere you want them to go. But number 8, last but not least, and is very important. For all vectors u and v, the scalar 1 times the vector u is equal to the vector u. Now, that might seem obvious, and it is obvious to us, having dealt with the real numbers and even the complex numbers, but you can make examples of vectors, of sets rather, where that last axiom fails to be true. Now, they're not useful, but you can do that. So it has to be satisfied. Now, let's begin by looking at our first example of a vector space. As you see there, V equal to Kn is the first and probably the most important vector space that we use in linear algebra, because that's where systems of linear equations reside. They reside in Kn. Now in 2260, we just used R n, the set of ordered n tuples over real numbers, but Kn is just the set of ordered n tuples where the elements are taken from the field K. And we know the normal definition of a vector in Rn, or here now Kn. As you note here, if you have two vectors A and B in Kn, A1 through An and B1 through Bn, we call those the coordinates or the components of A, and we define vector addition component-wise by adding the corresponding coordinates, and scalar multiplication, we multiply a vector by a scalar by multiplying every component or coordinate by that scalar. And then, of course, we know the zero vector is the vector whose every component is the scalar 0, with all coordinates equal to 0. Now, with this context, we note that Cn, the complex number Cn, is a vector space over the complex numbers, and Qn is a vector space over the rational numbers. But we can note that Rn, of course, Rn is a vector space over the real numbers, but Rn is not a vector space over the complex numbers. Why not? Look here at my notes. We would note that Rn is not closed under scalar multiplication if you take the scalars over the complex numbers. Indeed, if alpha is a complex number of the form a plus bi, where b is not equal to 0, and if x is an element of Rn, then alpha x is in Cn, but it's not in Rn. So it's not closed under scalar multiplication. And so, of course, Rn is a vector space over the real numbers, but it's not a vector space over the complex numbers. So it's important to know where we are when we're dealing with a field, a vector space over a scalar field. Okay, so next, let's continue on with our examples here. We see here on page 4 that in my notes we have the example, let V be an element of the vector space V. And here's our first proof of the day. Prove or show that the scalar number 0 times the vector V is equal to the 0 vector. Now here's the proof. It's a one-line proof, but you have to use the axioms of a vector space, okay? Now, the number 0 times the vector V. Well, let's add the vector V to it, and then employ the 8th axiom. V equals the scalar 1 times V. So you have 0V plus 1 times V. Then we employ the distributive property for scalars, and we take out the vector V, in parentheses 0 plus 1V, and then of course you know 0 plus 1 is 1, and axiom 8 tells us again 1V is V. So you have 0V plus V is equal to V. So then if you subtract V on both sides, you have now proven that the scalar number 0 times the vector V equals the 0 vector. And so now we have this additional property that you could call VS9, that you can now use freely, that not only is 1 times v equal to v, but 0 times v equals the 0 vector. Okay, now we're going to skip over to the next page, page 5, and look at now the definition of a subspace of a vector space. A subspace is, first of all, a subset W of the vector space V. Now, the notation that I use for a subset is the less than or equals mark. W is a subspace of V if the following 3 axioms are satisfied. Number 1 is closed under vector addition. That is, if V and W are elements of the space, that should be a W there on part I, and let me fix that instead of a V. Excuse me. If that should be W. If V and W are in W, then the sum's in W. And if V is in W and C is a scalar, then the scalar C times V is in W. And the third one says the 0 vector of V is also in the subspace W. Well, that immediately follows from the first two. See? For example, the 0 vector can be written as V minus V, which has to be in W by the first axiom. And the 0 vector we just saw a moment ago can be written as the scalar 0 times the vector V, and that has to be back in W by the second axiom. So a subspace of a vector space V, W of V, is a subset of V which is closed in itself under vector addition and scalar multiplication. Okay? Here's an example 2. Let V be Kn, and let W be a subset of Kn, where you have all your coordinates through xn minus 1, but then the last coordinate sub n is 0. Knock off the last coordinate. That is a subspace of Kn that we could identify with Kn minus 1. You're probably already familiar with the idea of dimension that we'll talk about later. Dimension of Kn is n, and we'll tell you more about that later. And of course, n minus 1 has dimension n minus 1. Now, one of the most important concepts in dealing in linear algebra and with linear equation is that concept of the linear combination of elements. Linear combinations. When you have an arbitrary vector space V, and you have a set of n vectors in V, V1, V2, dot, 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 through V sub n, and you have scalars, x1, x2 through x sub n, let those be numbers. And then you take an expression such as x1 v1 plus x2 v2 plus dot, 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 etc., plus xn v sub n. That's referred to as a linear combination. Now, a linear equation is simply a linear combination of unknown variables, x1 or v1 through vn, set equal to a constant number, as we'll see not too long in the future. All right, so here down below this definition in the text, there is a proof of a little theorem, or really a lemma. It's not even outlined as a lemma, but it really is a theorem. And I want to notice it with you just now in my notes here to the right. Theorem. Let W be the set of linear combinations x1 v1 dot 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 through xn vn. Then W is a subspace of V. It's called the subspace of V that spanned or generated by the vectors v1 through v sub n. And we see the proof of this here to the left on page 5 in our text. So we've got the scalars x1 through xn, so we need another set of scalars, column y1 through yn, and what do we have to show? We have to show that if we take any two vectors in this set W, that the sum of those vectors is in W, scalar multiples are in W, and that the zero vector is in W. So if you take two vectors that look like linear combinations of v1 to vn, add them together, and then by the distributive property, factor out the corresponding coordinate vectors, you notice again that the result is a linear combination of v1 to vn. Same thing with scalar multiplication. C times the linear combination, the scalar C distributes across addition, but then simply factor things out and you have that the result is a linear combination once again, v1 to vn. The closure axioms are telling you that if you take two objects in a set and you act on them with addition and scalar multiples, you remain in the same set. I have a little joke about that. If you add two dogs together, you get another dog. You don't get a cat, do you? That's the idea. When you add two creatures of the same kind, you get another creature of the same kind. So that's the idea of a closure axiom. Third, it's clear that the zero vector is in the set by simply taking x1 through xn to be 0. And so we see that the space of all linear combinations spanned or generated by v1 through vn is a subspace of the vector space. All right. Now, let's look at another example here. Now we're getting into something that you're already familiar with again, and that is the dot product or the scalar product of two vectors. And of course, you studied dot products in Calculus 3 in the context of 3 dimensions. Of course, the definition is the same, whether it's 2 dimensions, 3 dimensions, or n dimensions. And so here's my example, example 3. Let V be Kn, let A and B be two vectors in Kn that look like A1 through AN and little b1 through little b sub n. You probably know this definition. The dot product or the scalar product of A and B is the sums of the products of their corresponding coordinates or corresponding components. A1b1 plus A2b2 plus dot 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 plus A sub n b sub n. One can easily verify that these three properties, SP1, SP2, SP3, hold true for, this is called the usual dot product for Kn. First, it is commutative. A dot B equals B dot A. Second, it is distributive across addition. A dot B plus C is A dot B plus A dot C, or if you reverse it with commutative property, B plus C dot A is B dot A plus C dot A. And then the third one says it really doesn't matter where scalars are in a dot product. They can go in and out as they please. A scalar x can go anywhere in a dot product or scalar product. Note that A dot A is often written as A squared, but that's the only occasion that we use that notation. We don't use A cubed for A dot A dot A. And then we have the normal identities that you know in college algebra. A plus B squared is A squared plus 2AB plus B squared, and A minus B squared is A squared minus 2AB plus B squared. So we have our scalar product. So Kn is actually called a scalar product space because it has this scalar dot product on it. And it's the scalar product that allows us then to look at ideas like perpendicular or orthogonal. And again, you already know this definition. Two vectors are perpendicular, or orthogonal is another fancy word for perpendicular, if their dot product is 0. Now here's an example below that. Let A be a vector in Kn, and let W be the subset of Kn consisting of all vectors B and Kn whose dot product with the given vector A is 0. Then we can easily show that this set W is a subspace of Kn. And here's the proof of it. All right? Again, we have to show the three axioms for a subspace. Let B and C be two vectors in W, and let X be a scalar in the scalar field K. And then we have to look at addition first. B plus C dot A, that we know is distributive, is B dot A plus C dot A, which is 0 plus 0, because B and C are both in W. That's what it means to be in W. Its dot product with A is 0. And 0 plus 0 is equal to 0. So that means that the sum of B plus C is in W. Second, if we take a scalar and multiply it by the vector B that's in W, and take its dot product with A, then we can reassociate and pull that scalar out, and then take the dot product of B and A. And so you get X times 0, which is 0. So that means that scalar multiples of B are in the set W. And then third, it's clear that the 0 vector is in W since the dot product of the 0 vector with any vector is always equal to the scalar number 0. So that concludes that short proof. And there are other examples of that, one of which is a homework problem in the first homework set. Okay, next, a very important class of examples come in the context of calculus. Now, the next example here, example 4 in the textbook, as you notice on the left page, page 7, function spaces. Function spaces. Now, start by letting S be a set, any set, not necessarily a field or a vector space, but just a set. And then, of course, let K be a field. Now, by a function of S into K, we simply mean an association which, to every element in S, associates a unique element in K. Now, you know that that is the definition of a function in college algebra. You know, every X gets mapped to only one Y value. definition of a function. So every element of S is mapped or associated with only one unique element in the scalar field K. And of course, you're probably familiar already with the symbolism for a function f colon S right arrow K that symbolizes that f is a function that maps elements of S into the field K. We call this function a K-valued function. So if K is the real numbers, it's a real valued function. If K is the complex numbers, of course, it is a complex valued function. Now, let's let f and g be any two arbitrary functions, okay? Then we know how we add two functions together and how we multiply a function by a scalar. How do we add two functions, f plus g? Well, it's going to have to be done component-wise, as we see here in our lesson. So, coordinate-wise. So, f plus g evaluated at an element x in S is what? F of x plus g of x. And number 2, CF of x is the scalar c multiplied by f evaluated at x. And so that's the symbolism for the definitions of addition and scalar multiplication for functions. And with these definitions of addition and multiplication, the set of functions from S into K form a vector space. And for example, the zero element of this function space is just the zero function. I call it theta, and it is defined by theta of x is equal to the number 0 for all x in the set S. Now, let's look, as we're about to close today's lesson, at some subspaces of the vector space of real valued functions. Let V be the set of functions f from the real numbers mapping into the real numbers. Then let W be a subset of that, be the functions, real valued functions that are continuous over the real numbers. And then let U be the functions that are differentiable or have a derivative over the real numbers. Then it becomes clear that the differentiable functions are a subspace of the continuous functions, and that the continuous functions are a subspace of all real valued functions. That goes back to Calculus 1, where we say that differentiability implies continuity. When functions are differentiable at a point, they are then necessarily continuous at that point. But the converse is false, isn't it? Continuity does not always imply differentiability, does it? And the classic example is f of x equals the absolute value of x. It's everywhere continuous, and it has a derivative everywhere except where? The sharp turning point at 0, 0, where it changes directions, the V point. So at 0 is continuous at 0, but not differentiable at 0. And so you probably were not accustomed to thinking of functions as being vector spaces, but they are vector spaces. And then finally for today, here's another small example. Let V, again, be the vector space of all real valued functions going from Rn to R. And now let's take two special vectors, f of t equal e to the t, and g of t equal e to the 2t. All right? Let C1 and C2 be real number scalars. And then let W be the set of all linear combinations of those two specific functions, e to the 2t and e to the t. That is C1f plus C2g. I would suggest that you prove this for yourself for practice, that the W would indeed be a subspace of V. Do that for practice. Now, example 5 and 6 are a part of your turn-in homework that would be due on January 27th in the assignments tool in Brightspace. But example 5 tells us that if U and W are subspaces of V, then the intersection of U and W is a subspace of V. Notice the picture on the left side of your screen. What is that? In R3, that's the intersection of two planes, isn't it? And that picture shows two planes intersecting in a line. All right? And of course, we know they can intersect in just a point as well. And then example 6, that if U and W are subspaces of V, then their sum, U plus W, is also a subspace of V. Now, our first homework is on page 9, and I do want us to work towards 1 through 10, all of 1 through 10. Now, the turn-in homework in Brightspace is only number 7 and number 10. So you're going to hear this same lesson on Wednesday, January the 13th, but here it is in video form. I look forward to seeing you on our first meeting. So that's all. Dr. Hill is signing off.